We shall continue our discussion on intragranular corrosion of metals and alloys. We completed 2 lectures on intragranular corrosion of metals and alloys. If I can summarize what we have seen so far, we are, I suppose, clear on the definition of intragranular corrosion, right. I think you people should be very clear that it is happening at the grain boundary, selective attack taking place. Now, we said that among all the metals and alloys, stainless steel suffer extensive intergranular corrosion, especially when they are being welded, when they are not properly heat treated actually. So, in order to understand the intergranular corrosion of stainless steels, I gave very brief introduction to classification of stainless steels and the role of various alloying elements, how they affect the corrosion performance, right, we saw that. Then we went on to discuss the mechanism or you may call it as a theory of intragranular corrosion of stainless steels. Please notice that the intragranular corrosion mechanism may not be the same for all metals and alloys. So, we focused on what kind of mechanism operating in the intragranular corrosion of stainless steels and very specifically towards the austenitic grade stainless steel, okay. And if you recall, the major problem is the chromium depletion because of the formation of the chromium carbide, and that occurs in the selective temperatures in the range, let us say about 450 to about 850 degrees Celsius it occurs. But more importantly here, it is just not the formation of chromium carbide and the depletion of chromium as a result of the formation of the chromium carbide. But the chromium carbide formation is heterogeneous nucleation, it forms at the grain boundaries. So, it is heterogeneous nucleation. At the grain boundaries, and so the depletion of chromium is centered around the grain boundary area, and so the stainless steel at that area loses the stainless steel capacity to repassivate, to passivate. So, there is a selective attack taking place. The sensitization process we said was dependent on what? Dependent, of course, it is the chromium carbide formation, but what are the governing relationship there? The governing relationship there are the temperature, the time, the holding, or if you are going to cool it, the cooling rate. If you are going to look at cooling, it is going to be the cooling rate. These are the essential relationship that happens in the stainless steel. In essence, I can have a very high carbon containing stainless steel, I can still avoid sensitization provided I cool it fast enough to avoid chromium carbide formation. That may not be practical, but okay, in all cases, but you will see later it is possible in some cases. With high carbon content I can avoid sensitization. That means the factors that govern are the kinetics, okay. The kinetics are temperature, time, cooling rate. These are the factors that actually control to what extent the sensitization can happen, or if at all it can happen in a given thermal process. Then we went on to discuss the factors affecting intergranular corrosion from the point of view of the alloy, from the point of view of the metallurgy of the stainless steels. Started looking at it, and we said that of course carbon content is the primary one. You need to reduce carbon content. By no way you can simply increase chromium content and let the carbon content remain the same and avoid the sensitization process, okay. We saw that, we discussed that in detail. In addition to carbon content, there are other alloying elements can marginally influence this sensitization process. Some of them are beneficial, some of them are detrimental, okay. We saw, for example, nitrogen, is beneficial, chromium is beneficial, okay, tantalum, niobium are beneficial, whereas nickel is not good. So just look at the relationship actually. But one thing I forgot to tell there was that the nitrogen is beneficial over a range of composition. Somewhere I would say below 0.16 weight%. If I keep adding more nitrogen to stainless steel, what could happen? You can also form chromium nitride, right? You can form Cr2n, you can form Cr2n. That also you see here, one nitrogen captures to chromium, it can happen. But within the limited extent it can be beneficial. Then we looked at the grains, right, role of grains. After all, the sensitization occurs at the grain boundary area. So the nature of the grain boundaries affects the corrosion. So we said that the energy of the grain boundary, which means the energy of the grain boundary dictated by whether it is going to be low angle or high angle grain boundary. This has got low energy, so less IGC or no IGC, you can say. They got a high energy, you have high GC occurs. I do not say high GC because most of the material that you encounter, alloys and all, have high angle grain boundaries only, where okay. So we did not of course go in detail about the definition of high angle, low angle, but I just say that twin boundaries are supposed to be low angle grain boundaries. So if you have twins in the austenitic stainless steel, the twin boundaries will resist the formation of the chromium carbide, and so the sensitization process. In fact, these are important from the point of view of intragranular stress corrosion cracking. So stress corrosion cracking we have not discussed so far. Stress corrosion cracking can be assisted by the sensitization of the grain boundary, because the crack can travel along the grain boundary and make the metal more susceptible to cracking under tensile loading conditions. That part we will see later. Now we look at the grains, and we look at the grains from the point of view of energy of the grains. There is one more thing that we need to look at from the grains, continuing the grains. is that the size of the grains. You call a grain size of an alloy, right. Finer the grains, better it is from mechanical properties point of view. You can have high strength and toughness together actually, right. So what would happen? What do you think will happen if I reduce the grain size? I keep the composition same, the carbon content the same, the chromium content the same, even other alloying elements content is the same, but I reduce the grain size. So what do you think will happen to sensitization? Increase? Why do you think it will increase? The grain boundaries becomes more, it makes one way it makes some sense. But look at the other way around. The chromium carbide formation occurs only along the grain boundary. There is a limited carbon, right? The carbon content is limited. So you cannot form more chromium carbide than that is allowed in a given alloy, that is dictated by the carbon content, right. So assume that all the carbon is now converted to chromium carbide. Now I have a alloy which has got smaller grain size and larger grain size. So what will happen? Understood or not? The volume fraction of chromium carbide formation does not depend upon the grain size. It depends upon what? It depends upon the carbon content of the alloy, right? Right? I want to say that the volume fraction of chromium carbide formation is the same, but the grain size of the two alloys are different. One has higher, one has a lower one. So what will happen to sensitization now? So suppose like that. Now look at, visualize now. I want you to think. Yeah, but then over a time period, you cannot have more carbon, the carbon content is limited only, right. If you are going to have infinite source of carbon, then probably you will have more sensitization, right. Assume that the chromium carbide formation volume of 23 C6 is the same. Now I am distributing this chromium carbide over here and over here. So what happens? See, if you look at here, the overall grain boundary area, right? The grain boundary area in this area is more. Grain boundary area is less. Am I right? If you calculate the grain boundary area, I don't know, you guys might have studied this ASTM grain size and so the grain boundary area and all, right. So if the number of grains are increasing in a given volume, the number of grains are increasing, then the volume of grain boundary area, or I would say volume, the grain boundary area is more. So I distribute this chromium carbide here and here, the distribution becomes more dense here. So this could be less continuous distribution of chromium carbide. Here happened more continuous, I would say, continuous distribution of chromium carbide. So you will see that the grain boundaries are so well closely packed with the chromium carbide. Here it is not packed with the chromium carbide, because same chromium carbide has to be distributed over a larger area, right. So where is the attack? Where attack is more here. crack is less here. So, lower the grain size is beneficial from the point of view of sensitization. But please notice it is not a overriding factor, you know, I can't keep the carbon content at 0.08 and lower the carbon content, keep the carbon content at 0.08 and then lower the grain size. Yeah, it can have some effect, but it is not going to have overriding effect, right, please understand that, okay. But it does affect the sensitization because of this particular factor. So, the depletion of chromium is more in the grain boundary areas of the larger grains as compared to the depletion of chromium over here, okay. So, you find the smaller size are better from sensitization point of view as compared to the larger grain size in an alloy. I hope you get this idea, right, or still anybody has any problem, okay. The next part that I would like to talk about is role of crystal structure. We saw earlier we classify stainless steel as austenitic, ferritic, martensitic, duplex and precipitation ornamental stainless steels. By nature the precipitation ornamental stainless steels do not have very high carbon content, the carbon content is very low. The strength of that stainless steel comes from where? Comes from the alloying elements, right, like aluminum and copper, they form precipitates, they give rise to strength. So, the carbon content of that is very low. So, the remaining ones we should look at how these class of stainless steels perform with respect to sensitization. Let us take the ferritic grade. Let us look at the ferritic grade now and see how it performs. If you take an austenitic grade and ferritic grade, which one will suffer more, or what is the tolerance of carbon when it comes to ferritic stainless steels? Suffer more, right. So, what is the solubility of carbon in ferrite as compared to austenite? So, ferrite dissolves very low amount of carbon, right. So, it cannot saturate more. So, that means when you are going to heat it, it is much easier for the carbon to precipitate into chromium carbide in the ferritic stainless steel as compared to the austenitic stainless steels. So, the solubility level of, because you know isn't it, for FCC structure the solubility of carbon is always more as compared to a BCC structure of steel, right. So, you find that, okay. So, that means here it is a poor carbon solubility. So, in this case even nitrogen is detrimental. So, we can say that carbon plus nitrogen has to be less than 100 ppm. So, what sometimes people do is they add some titanium, some stabilizers, titanium is added to stabilize. Okay. Of course, modern ferritic stainless steels have very low carbon, I mean there is no problem, but even then you can add some titanium, it becomes easy. But there is always a problem in the low carbon varieties, right. when you weld, you can pick up carbon from the surrounding. Suppose you have some grease or something, right? You weld it, the grease gets converted into carbon on when you strike an arc and carbon gets into the material, right? So ferritic stainless steels are more problematic compared to the austenitic grade stainless steels. Austenitic we have discussed very extensively before, right? Here the carbon content can be less than 0.03 8% because the solubility of carbon in the austenite is better as compared to this. Let us take the case of martensitic. Martensitic stainless steels are generally containing higher carbon content, right? Why need a higher carbon content? Yeah, it forms a martensite, and secondly that is what gives hardness also, right? So in order to form martensite, you need to have reasonable carbon content. Without that you cannot form. So the carbon content of martensitic stainless steels are higher compared to austenitic grade, of course ferritic grade actually. But even then they are less susceptible they have higher carbon, in fact highest carbon among all the stainless steels. They are less susceptible to IGC. Can you tell me why? Yeah. The martensitic stainless steels are used in what condition generally? Or martensitic steels generally what condition you do? You use it in fully martensitic condition? How do you do that? Tell us this. You temper it, na? If you don't temper it, then what happens? Then it becomes so brittle, the toughness is so bad. So when you temper it, what happens? They form what? They form carbides, right? So they form carbides. In fact, the martensitic stainless steel also form carbides actually. Without that you can't temper it, right? So when you go to temper it, they form carbides. It can form chromium carbide, it can form iron carbide, but preferentially it forms chromium carbide because the chromium carbide is more stable as compared to the iron carbide. But even then I say it is less susceptible to IGC as compared to austenitic grade. Why do I say that? Have you heard of tempering martensitic steels? Forget about stainless steel for a moment, right? Tempering of martensitic steels. Anybody? Have seen the microstructure of tempered martensite? Tempered martensite microstructures. Anybody seen? No? That's sad. Huh? Then you can't get an idea about what it is actually, right? When you take a martensitic steel and you solutionize it, take it to austenitic region and then quench it, you form a martensite. When you temper it, how does the carbide form? The carbide forms within the martensite. What is the martensitic phase? It is actually it's a BCT, right? Martensite is a BCT structure. We saw it before, right? And this is the FCC structure, right? And this of course is a BCC structure. So it is a distorted lattice. So much of carbon is saturated now. It is not martensite is single phase. So when you heat it, it forms carbide. But how does the carbide form? The carbides form within the martensite. Martensite is given by a term called alpha prime. So you have more or less uniform nucleation. This is not a right term to use, but I will use it. So the grain boundary precipitation of chromium carbide is very less here. So, the chromium carbide occurs all through. Okay. Now, please understand IGC occurs only when the chromium depletion occurs at the grain boundary area. That will happen only when the chromium carbide forms at the grain boundary area. If it forms everywhere, IGC does not occur. Of course, the chromium carbide formation by itself can bring down the passivity. We know that, right? Because the matrix chromium content comes down, passivity is lost, I am sure. But the issue here is we are talking about the IGC, we are not talking about the overall loss in the passivity. In fact, the modern synthetic stainless steels, when they temper it, they temper optimally so that you do not lose too much of passivation. If you do not temper it, it is brittle. So, they temper it optimally in order to have good passivation, at the same time good toughness actually. So, there is optimization process. So, coming back to the point here, the modern synthetic stainless steels are not prone to IGC primarily because of the fact that the chromium carbides form within the martensites. Okay. And so, the depletion of chromium, the grain boundaries or lath boundaries, whatever you can call it, okay, acicular boundaries, whatever you can call it, is less. But of course, if you keep on aging for a long time, they also can undergo intergranular corrosion, but generally they are not prone to intergranular corrosion. So, please understand the concept of intergranular corrosion in a proper manner actually. Okay. So, it is not the chromium carbide formation alone is responsible. The chromium carbide formation of the grain boundary and the consequent depletion of chromium of the grain boundary is responsible for the intergranular corrosion of stainless steels.
Why does chromium carbide precipitate inside martensite?
It's a good question. Okay. Yeah, then I think then you have to go into the metallurgy aspect of what is called a nucleation and growth. See, martensite, what is the martensite? The martensite consists of a lot of dislocations, most of you know about it. That's the reason why it gives you higher hardness, higher strength. So, when you have a lot of dislocations within the martensite, when you do annealing or aging process or tempering process, what happens now? The precipitations occur on the dislocations. The dislocations are large in number within the martensite. So, they preferentially precipitate along the dislocation. That is why when I say uniform corrosion, I say within quotes. It is not really that uniform corrosion. I am sorry, when I say it is uniform nucleation, I do not mean in true sense of it. Okay. The true sense means it should not happen at the dislocation also. But because you have a lot of dislocations, martensite, and so they are very well uniformly distributed in the martensite. So, you have lots of chromium carbide being precipitated there only. Okay. So that is what happens in the case of martensitic, the stainless steels. Any other question? Let us get into the next class of stainless steel, duplex stainless steel. The duplex grade, when we talk about, we say it is a mixture of alpha and gamma, each of them in 50 volume percent each. It is more resistant than ferritic and austenitic grade. It's a very interesting thing actually, right. Ferritic stainless steels are more prone to sensitization, austenitic stainless steel is also prone to sensitization, but you have two phases in the alloy, they are better than both of them actually. Okay. And the reason is not very difficult to understand actually. Okay. Let me draw some diagram. So, this is an alpha phase and this is the gamma phase in a duplex stainless steel. Okay. The precipitation of the chromium carbide occurs here. The grain mode, I just take only one precipitate here, it occurs here. Very interesting thing happened. Chromium diffusion in alpha is much faster than in gamma. Carbon diffusion and the solubility both are high in gamma phase. Look at how the cooperation takes place. So, you have here more carbon, isn't it, because the solubility of carbon is more here. If you take alpha phase and the gamma phase in a given alloy, can you guess which would have higher chromium content, will the alpha or the gamma? Is chromium is what stabilizes? Is it gamma stabilizer or alpha stabilizer? I mean alpha stabilizer. Also, so come on, yeah, you should be able to tell, right? So is a chromium it has got a higher chromium level here, isn't it? Partitioning taking place, in fact, it will have more chromium. It may even have more molybdenum also. Anyway, that is not important for us. Look at it. So you will have more chromium here, and the diffusion of chromium is higher in alpha, higher carbon. Now what happens now? The carbon diffuses here fast and chromium diffuses fast here. So what happens? Now if it happens now what happens? As a consequence, chromium depletion is minimal. On both the sides, because when you have faster diffusion, then what happens? Then you do not get a strong concentration gradient, right, quite fast, and there is no need for the chromium in the arsenic side to diffuse, because when the carbon goes over here, the chromium moves from alpha to form the chromium carbide, right. So that means the grain boundaries are not going to get depleted so much as it happens in the ferrite or it happens in the austenite, right. So that means what happens? So it is minimal, and so IGC is minimal. So duplex stainless steels are generally more resistant to IGC as compared to austenitic grade and ferritic grade. Of course, modern static stainless steel, the issue does not come into picture because they nucleate in the grains. Of course, there the corrosion resistance of modern static stainless steel falls because of the tempering process. Okay. So this is about the crystal structure. You have seen how they affect the sensitization of the stainless steels. Okay. So this should be known to you. Any questions here? Right. Okay. So let's move forward. Effect of cold work. Effect of cold work, when you do a cold working, what happens to the material? Torque dislocations, right. So cold work at a low level increases IGC because dislocations easily transport carbon actually, right, easily transport carbon. High level of cold work lowers IGC. Anybody can guess why at high level IGC is getting reduced? Yeah, you have lots of dislocations now. In fact, they get entangled. So because they promote chromium carbide precipitation within the grains. Of course, see the overall passivation, all this will come down. We are talking, please again don't try to club everything together. We are only talking about IGC. I am not saying that cold working is better for overall performance of stainless steel. No, that is not the idea here. Okay. So this is about the intergranular corrosion, the theory, the factors affecting the intergranular corrosion of stainless steels. We have seen so far, and any of you have any questions, you please let me know.
How does dislocation facilitate diffusion of carbon but not chromium?
Yeah, see when you do that, when you see what happens is when you do cold work and you anneal it at temperatures, the dislocation gets annealed, they go to the grain boundaries and all, right. So the dislocations move and carbon can go along with the dislocations, isn't it. So it facilitates the movement of or diffusion of carbon to the grain boundary. Okay. So of course, it is not going to facilitate that much of chromium because see, and carbon is so small atom, it get entangled with the dislocations, right. Okay. So let us now go to the main topic of weld decay. Okay. This is the real problem in industry. Okay. What you have seen is signs of that. It's a real problem in the industry. I am going to show you the one diagram. Okay. Not a diagram, it's a photo of the weldment. Okay. Get back to this here. You weld a stainless steel, and it is what is this? This actually is a TIG welding, and it's a butt welding, right? It's a butt joint, right? What do you do in a TIG? What do you do in a TIG welding? You strike an arc, right? And you use a filler wire. An arc is stuck between the metal and the electrode, right? The temperature is so high, it melts. It melts the electrode. Either it's a consumer electrode, for example, or use a filler wire. It melts, and then they deposit and they join. That's how you do fusion welding. You do that. Okay, it's a thermal welding here. So you have a TIG welding, you have a MIG welding, you have laser welding, you have electron beam welding, you have brazing. There are several kind of metal joining techniques. They do exist. In all these cases, what is common is the joining process is due to the thermal process. They melt and the union between the two pieces they occur. So stainless steels are being heated now, and the molten things join them together. Now what is very interesting, you look at this diagram here is, the highest temperature, this is the highest temperature. And here the lowest temperatures. the temperature starts decreasing from here to this onwards. Temperature decreases. Okay. Though the maximum temperature is here, the sensitization does not occur at the fusion zone, it occurs away from it, which is called as a weld decay zone, generally termed as a heat affected zone. Actually, the heat affected zone is generally categorized as what? That zone where there is no melting takes place, but there is some solid state transformation, metallurgical transformation occurs. Over here, the so called metallurgical transformation occurs only here, not even here also, it happens here. It does not happen here, of course, lower temperature nothing happens. Now we need to understand why it happens here, why not here, why not here. Also, we need to understand why can it move towards left, can it move towards right. If so, what happens? That means you need to understand clearly what governs the formation of the weld decay zone. That is very important for us to do that. We have seen the science of it. We have looked at the interrelation between the metallurgy of the alloy and the time and temperature cycles, that you have seen that actually. So with that we try to understand this particular phenomena of weld decay. Okay. Now let us go back. Sensitization is temperature dependent and time dependent, composition dependent. Can I make a statement like that? Okay. So now let us see why should the weld decay occur at the heat affected zone. Though that is the first discussion that you are going to make it. Let us take a schematic of this. So plain view it is. Okay. Now when you weld, if I keep a thermocouple here, or if I keep a series of thermocouples here up to this point, what I can follow? I can follow temperature rise and fall with respect to the time. Can I do that? So when I start welding from one end to another end, put a thermocouple there and monitor the temperature with respect to time. If you do this, very interesting thing can be observed. I am going to give you a very schematic of the temperature variation with respect to time, say at location A, say fusion zone, and this is the heat affected zone. Let us take the fusion zone. The maximum temperature will be at the fusion zone, right? So what happens now? The temperature shoots up, something like that, something like that it goes actually, right? What is this temperature? It is well above the melting point of the alloy that we are talking about, right? 1600 beyond that, okay. Let's take this zone here. Something like that. This is the fusion zone, this is your weld decay zone, and this is your base metal. Somewhere here. Now let us identify the weld. Let's identify the sensitization temperature regime, that is between 450 and 450 to 850 degrees Celsius, right. So you have between 450 somewhere around about, let us say 600 or 700 or maybe 1800, temperature is quite high temperatures. So between these two temperatures, the alloy will form chromium carbide, provided what? Provided you give enough, I think you are forgetting that, right. It may sensitize between 458 850 this temperature region, provided you give enough time. If time is not sufficient, then the guy is not going to give rise to chromium carbide precipitations. Now let us look at the eta vector zone. Now I am going to now look at sensitization. I am going to draw a small temperature time sensitization diagram for you, because you need to also know this, right. What is this temperature? Around 850. What is the temperature? 450 degrees Celsius. If I take it to this temperature and quench it very fast, no sensitization, right. Or I put the other way around, if I can draw a nice thing. Okay. Look at this. This is the maximum time that is allowed for the material to cool down, right. When you hold it in the gamma, this is what this is called gamma regime, right. This is gamma regime. This is the maximum time allowed to cool. If you go beyond that, what happens? Chromium carbide forms, right. So when you take it to this temperature, if you are going to cool it faster than this, that means less time, no problem. Slower than that, you are getting into sensitization. That means the time that can be held in this temperature, in fact this region, right, or actually speaking you should go from here. If you really look at it, this is the time and this is the time, am I right? Time it starts from here and goes here, right. This is the time, right. If you draw, in fact more appropriate way of talking about is what? This is the delta T, I hope you get it, isn't it? Time taken starts from here, right, up to this temperature is no problem, after that it starts. So this is the delta T critical temperature, critical time required to avoid the sensitization, right. So this is delta T here. Now look at this look at this this curve. I have started from here, this is the time it started, and time that ends is here, this is the time that ends. So, this is the delta T that I have here. Assume that it forms the chromium carbide. Even chromium carbide forms when you raise the temperature above, what happens to chromium carbide? Dissolves, right? So, it dissolves. So, this time is not counted, because when temperature goes up, the chromium carbide dissolves. Now it starts counting from here and then count from here, right. So, this is the delta T, the fusion zone, am I right, where the material is held in the sensitization temperature region, am I right, isn't it? It starts at this temperature, it ends here, because below this no problem. So, this is the time it has been kept in the temperature region of 450 to 850, right. If this time delta fusion is going to be smaller than delta T critical, what happens? Yeah, this small t, no? Oh yeah, I am sorry, yeah, thank you very much. Yeah, if it is within that, then there will be no sensitization, agreed? Now let us take this case of E temperature zone. You guys are okay? Now let us take the case of E temperature zone. It starts from here. Where does it end? It ends here. Delta T, it says that. You guys follow or not follow? Okay. Now if you look at here, it becomes so obvious for you, it becomes so obvious, you will find at least delta T fusion is much smaller than delta T H says that. Can you make it? You get it from this diagram? Now what happens in the case of base metal? Yeah, it does not get into the region at all, so there is no sensitization. So the sensitization of the E temperature zone is quite understandable, right, because the time that E temperature zone resides in the sensitization region is good enough to form what? To form chromium carbide precipitates to get sensitized. So the E temperature zone is prone to sensitization. This is the thing that you should be looking at. What is the thickness of this delta T? It only says that when you weld it, the fusion zone goes through the sensitization regime from 450 to 850 for this much time, okay. It may not sensitize, even it sensitizes, assume that if this delta T is much larger, assume that this delta T is much larger, even then what will happen? Because it goes through higher temperature, that will get dissolved, the chromium carbide get dissolved. So that means this one anyway has no significance from the point of view of welding, right, there is no significance. I am only trying to analyze the thermal cycles during a welding process, okay, but otherwise this one does not have any significance at all, because even it gets sensitized, for argument's sake, if you make it, they get dissolved when the chromium carbide when the temperature exceeds the solubility of the chromium carbide precipitate.
Why you are taking in case of the heat affected zone at the temperature 450 degrees Celsius,
Yeah.
taking delta T from that point to that point, that is.
Yeah.
But in case of fusion zone,
Yeah.
The same well thermal cycle, cutting 450 degrees Celsius at 450 degrees Celsius at 2 points.
Yeah.
But in that case, we are taking only little time.
It's a good question, okay, but I want somebody to answer. Yeah, here look at here look at this. I start from here, the temperature goes above, it is still within the 850, right. So what happens? The alloy continues to transform, continues to form chromium carbide, right, until it reaches back here. That means all this thermal cycle, the alloy is subject to heating, which means chromium carbide will continue to form, right. If it goes above this only, what happens? Even there is a chromium carbide forms, they will start dissolving, right. So if this, assume that this curve goes here, then what happens? I would again will take only the second half of it, or put it other way around, these portions you see here, see this is thermal cycle for this, right, this is for that. Now I can have a series of thermal cycles starting from here to this, many of them are in between things, right. Can you visualize that? What will be the thermal cycle for this? It will be somewhere here only. This guy will go the time is more, it is more than this, okay, but then the guy has gone up. So if I have another thermal cycle, the guy again exceeded here, right. So the guy dissolves. If it does not dissolve completely, of course, then you can count it also. I mean, it is not that no hard and fast rule, but that you need to make a calculation and see what happens at all. Okay. So what we are assuming here is that when it goes up, the chromium carbide dissolves. Actually, dissolution of carbides are much easier than nucleation. If you look at generally, dissolving is much easier. It does not require that kind of normally overheating is not required. When you melt it, you do not need a overheating. When you cool it down, you need a undercooling because nucleation growth is a problem. But apart from that, okay, you can able to calculate and see what really happens in the thermal cycles actually. Yeah.
How when the delta TF is smaller than delta TC, then the sensitization does not occur.
If delta
TF is smaller than delta T critical.
Yes.
Occur, but
Yeah.
why if delta THZ it occurs sensitization?
That's what, no, you see here, the fusion zone, it starts from here and ends here, right. This is the delta T fusion zone, right. If that, and generally this time is very small, right. You see, what all I am trying to say is that, assume that I am going to take 304 of 0.3% carbon, okay, filler wire, suppose I take hypothetically. Do you think they do not sensitize? It may sensitize. Why? The time required to form chromium carbide decreases when the carbon content is increasing. So when you are increasing the carbon content, even the fusion zone also can form chromium carbide provided the carbon content is very large. But the carbon content of the fusion zone is almost equal to that of the base metal. So it requires same amount of time for the formation of chromium carbide. Okay. So you need to understand from the point of view of again temperature time cycles. Okay. So chromium carbide formation, the temperature time required is the same whether it is in the base metal, whether it is in the heat temperature zone, whether in the fusion zone. I am not looking at other small variations like I am not looking at all complications arising out of nucleation growth and all. Generally, you would say that the time temperature required is same. If that is about the case, then the fusion zone by inherently will have less time in the sensitization region as compared to the heat temperature zone, because heat temperature zone never crosses the solubility regime of that actually, right, it does not go up. That is the reason why it is happening at all. Any questions? This is a good question. If people asked, I think that also brings you clarity in terms of understanding what is happening in typical welding of stainless steels. Can we now move? So, what it means to us actually? It means to us that we understand the science of welding in addition to the science of sensitization. What is science of welding? How much heat input I give to the weldment. It all depends upon how much heat I deposit on the weldment, but that decides the cooling rate, right. Suppose I have a weld, somebody welds like this sheet, somebody welds like this. This is called as a narrow gap welding, kind of things. Somebody welds like this. The heat input required to fill here, because you are going to deposit so amount of molten metal here, you deposit small amount of molten metal here. The cooling cycle here and here are different, so the way they sensitize are going to be different. Am I right? Similarly, the conductivity of this metal and this is different, things will be different. So we need to superimpose the sensitization kinetics with respect to the science of the welding process. Then only you can able to understand how the weld decay occurs, right. So this probably is taught very well in the welding course. I do not know how many of you have taken the welding course. There you will go through much rigorous treatment of the welding and all the things. We will not go through that. I will give you very minimal things to appreciate how the welding processes can affect sensitization, weld decay in addition to the alloy chemistry. Now let us take the cases of types of welding. Okay, I am going to now look at types of welding into that. Okay. Now we know we can look at an arc welding, we can look at laser welding, can look at electron beam welding, can look at the gas welding. How many of you have taken a welding course? Okay, for you guys must be very simple actually, it's not that difficult to do that. Okay. So before we get into this, let us look at some simple properties of this. Let us look at the heat input. Maybe in terms of joules per mm square or whatever, right? Isn't it? Something like you give it, right? Let us look at the heat input required to weld in the case of arc welding, laser welding, electron beam welding, gas welding. So how do you consider that? Which one is the highest here in this? Heat input required to weld. I am not talking about the power of the welding, I am not talking about power of welding, right. I am talking about heat input required to weld, this much area required to weld, right. That's what I mean. So you should not confuse between these two, right, isn't it? Okay. So gas is the highest. Which is the least here? Electron weld welding is the least. It is the second least. This is the third least. It's not the right way of defining. I should put number 1, 2, 3, but anyway, I hope you can understand this better actually. Okay. So these have a consequence like this. So I want to weld This is a cross section actually, it is a cross section, maybe let us say about 3 millimeter I want to weld, and of course you can, if you want, you can draw this also, right. Something like that you can weld. So I keep welding using many of these techniques. If I take a, if I take the so called E temperature zone, okay, and I measure the thermal cycle, schematic only, not very this thing, right. Now can you map these thermal cycles versus this? Yeah, the first one is the electron beam welding, great. Second is the laser, third is arc, and fourth gas welding, fantastic. Now we can now see that what is the role of the welding technique on sensitization of a stainless steel. Can you or can you not? Okay. Now I want to, let us say I have 0.02 weight % carbon, okay. I have 0.8 weight % carbon, 1 and 2. I have 0.02 weight % carbon and I have 0.08 weight % carbon. I welded this one, I did not get sensitization. I welded this, I got sensitization, okay. I welded the first one in one of these techniques, I found it is weld decay, sensitized. I used one of these techniques, I welded this, even then it did not get sensitized. Can it happen? Good answer. If so, you tell me the technique that led to no sensitization, electron beam welding. There you go, right? And I use this still got welded a problem. Which is the technique? Gas technique. So they are not science. So you need to understand the sensitization in terms of that. It's not in abstract terms. You translate the sensitization kinetics in terms of the welding techniques, then you can able to appreciate it. And if I want to weld it, so what happens? Essentially the cooling rate, right? Suppose I use a TIG welding, I have 0.05 weight % carbon, I do not want to sensitize, it is a 304 stainless steel, 0.05 weight %, I do not want to sensitize. What I should do? Yeah, possible, but yeah, of course, I mean it's good answer I would say. When you increase the welding speed, what happens now? The Q goes up, but the problem is you need a minimum Q in order to fuse, otherwise it will be a improper welding, right? Okay, so that may not give us a good welding. Okay, now what else we can do? I can think of cooling it, right? If I can think of cooling the system, right? I think of cooling the system so that the cooling, so that the rate of cooling becomes faster. So, you need to look at it from the point of view of that, okay. There are so many variations that you will get, there are people, okay. So, this should be seen in that light so that you can understand it better. So, it is not simply that look at it in abstract sense, you need to correlate the process parameters with respect to metallurgy and then see how we can able to control weld decay, so that in practice we can do that. Same answer that you have been giving, the people have found TIG welding 0.038% carbon, sometimes they found there is no weld decay, sometimes they found weld decay. Why? It is manual welding, the guy got so tired, he was not welding very fast, he started slowing down the torch, okay. Then what happens? More heat input, got sensitizing problem. So, it does not guarantee you that no sensitization taking place at all, okay. So, that is how you need to analyze the problems. When you go to industry, problems are complex, but what gives you the way analyzes the scientific understanding to see, you find carbon is same, low carbon, why does it happen? So, you need to understand why things are really happening the way they are happening and how to find a solution to the problems. I will stop here, okay, and I hope we will finish this IGC when I go on to meet in the at 5:30, right, 5:30 I will finish up that actually, okay. And meanwhile, if you have any questions, you please let me know how we can clarify those doubts actually, okay. So, thank you very much.